If you've recently worked with Rust, you've probably come across code like this and this. And depending on what level of experience you're at, you might perceive such code in different ways. While the code itself is perfectly fine for demonstration purposes, it often teaches more inexperienced Rustaceans an unhealthy relationship with unwrap and error handling in general. But gladly, we can fix that. So let's jump into a small presentation of error handling in Rust and why unwrap is no method you should ever use in production code. Rust is a pretty special programming language because it knows neither null pointers, at least in its safe subset, nor exceptions. That's quite a stark contrast to a lot of other mainstream languages. The potential absence of values is modeled with the option enum, and potential errors are modeled with the result enum. The system makes a lot of sense because it eliminates two whole classes of common errors: accidental null pointer exceptions and unhandled errors in general. Rust forces us to handle all possible states of an operation, which is enforced by the type system and doesn't rely on common sense like in other languages. But it's important to notice that Rust's system doesn't lead to a lot of additional unnecessary code that we wouldn't usually write elsewhere. In fact, it actually transparently shows that we are probably taking shortcuts in these other languages that we just should not take. Rust's system isn't completely closed, however, because there is an escape hatch: panics. The language itself describes panics as another category of errors: unrecoverable errors or bugs in our code. A panic leads to the termination of all our program's threads and the program itself. For most software, that's often an undesirable state to be in. We don't get a good chance to clean anything up or do any necessary work before the program shuts down. Our software just dies, and depending on the kind of software it occurs in, that panic might be more or less convenient for its users. A CLI terminating with a panic isn't great, but at least it's only a CLI that's often just a one-off run. A microservice terminating with a panic, however, is already far worse, because it potentially can't serve any requests during the time it terminates and hopefully restarts. That microservice example is such a bad scenario for software, by the way, that there are even ways to catch panics and prevent a service from shutting down uncontrolled, which tells a lot about how serious panics actually are. But hey, do you know what's better than to drown in theory? To do something practical. So let's create a small example to experience different states of errors in Rust and how to deal with them. Let's imagine we are building a small parser for key value records. All keys and all values are simply strings, and a record can be represented as a string with an equal sign in between. We can create a small struct to represent our record and give it two string properties for its key and its value. If we now want to parse a string into our record, we need to spend some thought on how we want to create a good API to do that, and which issues we could eventually be confronted with. Strings can contain an infinite amount of possible combinations of characters, but we can only work with a limited subset of those. In fact, we need only exactly one equal sign within that string, and the rest is completely irrelevant. But what if we receive a string we can't process? Well, for us, that's nothing to worry about. It shouldn't let any program crash, at least from our perspective. We don't need to continue processing some broken input, and can instead just opt out if that happens by returning some kind of error. That makes this operation fallible. It's something that can fail in a controlled way. It's, by the way, important to notice that for someone else, us not being able to parse their input might be a reason to even crash their program, because errors are always a matter of context and perspective. However, Rust has a built-in trait for fallible conversions, called try-from, and we can implement try-from with the generic parameter string slice for our record type. The trait has an associated type with which we can specify the error type of our result. We could now just use a string for our error, and for the simplicity of our small example, that would probably be enough. But a good API design also includes senseful error design. A string is a too generic way to tell someone that something went wrong. A dedicated error type, on the other hand, gives us more ways to attach meaningful information to errors, while giving users of our API the chance to actually test for different errors. such that they can decide on how to deal with this undesirable state themselves. So let's create a new enum and derive error for it with the help of this error. This macro basically implements the error trait from the standard library for our enum and thus makes it compatible with a lot of base logic everywhere. After that, we can add a new enum member and call it malformed record. It takes a string property and is headed by this error's error macro, which automatically derives a display implementation for our member, including the message template supplied. Now we can focus on implementing the parser. Let's start by adding one of the most elemental checks we will need, testing whether the input contains an equal sign at all. If it doesn't, we can't really continue, because we already know that we don't have a valid record at hand. For us, it's basically expected that things like this happen. We don't need to panic simply because we got an invalid value. We can just transparently return to the caller that we can't process that input, and we can even give them some context with our error type by hinting at the fact that the record is malformed. The next thing we can do is to split the input at each equal sign and then map the resulting iterator items and trim them so we remove surrounding white space. We can then convert the resulting string slices into own strings and collect all that into a vector. After that, we can implement another small piece of error handling. We already know that we have at least two elements within our vector because the guard statement at the beginning would have led to an error being returned if the input contained no equal sign at all. This means that we deal with at least one equal sign, but we can't yet know for sure that there aren't more. And if there were more, the input would also be malformed. As we have a vector at hand, we can simply check how many equal signs there were by testing whether that vector contains more than two elements. If it does, we can also return an error with our malformed record error. Now we know that we have exactly two elements within that vector, a key and a value, and thus we can extract both. We can get the key by calling first on the vector to get the first item, but that returns an option, which leads us to another case of undesirable state we can encounter in Rust. At this point, we are sure that this call cannot fail, but the APIs of a vector are of course generic, because they need to work for all use cases. These use cases include that a vector is empty, which is when a call to first, for example, would return a none. The type system, however, has no connection to our code. It cannot dynamically change based on the context of the code some function or method is executed in. So this is basically a case where we know something better than the compiler. We could now just unwrap the value and definitely get the key of our record, but that would not be the best way to deal with it. We are completely correct in our assumption that this call cannot fail, so it's completely fine to leave an option's guardrails behind and just escape from it. But we can only safely escape from the option because of other code we've written. Right now, splitting the input string ensures that we definitely get one entry within our vector. Even if the string contains no equal sign at all, split would simply return the full slice, and that makes one item at least. If we or someone else were now to change the method of how we exactly try to retrieve the key and the value from the input string, that call to first might actually panic in the future if we try to unwrap it, and that would then become a bug. So we found a case of an unrecoverable error in very specific circumstances. Additionally, if an unwrap panics, it only gives us a very generic error message. An end user can usually do nothing with messages like these, and even other developers are left clueless and forced to dive into our source code to find out what happened, and that's bad. A better way to still unwrap our definitely available key is to use expect, which acts exactly like unwrap but gives us two additional features. First, it allows us to specify a good error message that can actually be helpful and tell someone that we have a bug, not them. And second, it marks intention. The name of the method already says, I expect this to be there. And it additionally implies, if it isn't there, I made a mistake. That's some very good information for anyone reading our code, asking themselves why we did certain things the way we did. And lastly, it's a great example of good self-documenting code. Good. Now that we know that, we can just extract our key by adding a call to expect after the call to first. and add a good error message that explains that this should not have happened, should it ever panic. If we now want to extract the value, we can use get1 to get the second element of the vector, and that returns an option once again. This case is nearly the same as the first one, but this time it depends on two other statements to continue working. Splitting the input ensures that we have at least one element, and the first guard statement at the beginning that ensures that there's at least one equal sign guarantees that we have a second element that we can now extract. If only one of these two statements is somehow changed, it's also no longer guaranteed that we can extract the value at all, so we have another potential bug waiting to happen. In the end, we can handle it like the other case though. We can expect the value, marking our intention again, and providing a good error message for the case that our statement ever becomes a bug due to carelessness, for example. After that, we can return an OK with an instance of our record struct, and that's it for our small parser. Admittedly, that was only a very small example, and out in the wild, we can find way more nuances to everything that we've gone over here. But we can still derive a few general rules for error handling in Rust from it. Letting a program implemented in Rust panic is never a good idea. There are ways to delay or even prevent a panic, like catch unwind, but they should be reserved for software that really needs it. In the end, the language itself states that panics are a last resort and more often than not, simply bugs. A web server, for example, might delay panics to clean up resources or close connections to upstream services that are still open. Or it might even prevent a shutdown completely, but that's a very special case which usually has very good reasons. In general, we should use result to mark and handle states of failure, and even our CLIs can just return an error in their main function and gracefully shut down if something fails. That also allows us to add better error messages for users than the default message you get when a panic occurs. If done right, handling errors correctly can sometimes lead to a lot of code, but that's also the complexity of the situation then, and not an issue of Rust. We can still circumvent some of that when matching results if we only handle the generic error case, without taking a look at the specific error returned. But regularly, that's not what we should do, because it's often also just a shortcut. The same goes for options. We usually need to handle the absence of a value accordingly, and either return a none to the callers of our function, deliver a default value, use one ourselves, or else. And regarding unwrap, using it outside of test code is never a good idea. At a point we need to use unwrap, we've usually navigated us into a situation where the type system can't keep up with our actual implementation. We are thus about to introduce potential future bugs into our software by using a method that can start to panic the moment just a small condition in our code changes. Unwrap also produces a terrible error message if it panics, and its usage is ambiguous. We never know exactly whether someone placed a call to unwrap intentionally or just forgot to handle all necessary cases if we encounter one. A call to expect, however, carries more weight, as it additionally sets a statement. And it often even makes sense to add a comment above it to explain which conditions prevent the panic from happening, so that someone refactoring code or adding features to it at least has a chance to find out what to look for. Whew, that's it for this small opinionated presentation about errors and their handling in Rust. I hope you learned a thing or two, and maybe you'll use some of that in your next project. This video, however, it's over now. What are you still doing here? See you in the next one.